Okay, so today we're happy to have Gabriel Cuomo to tell us about custom impurities.
Okay, hi everybody. Thank you for being here. And thanks for inviting me. So today I'm gonna be telling about some work that I did almost years ago with Ilchen and Zoe, and some work in progress with Simone and Luigi. The plan is that we will have some motivation. Then we will discuss the main object of interest in opinion signature. I'll explain why this is interesting. And then finally, we do the same thing in Lorentz signature. So, yeah, I don't know how much should I give an intro to this topic here, but it's still very worth saying. Intro, motivation. Okay, so as the title said, the talk is about impurities. So I really mean by this today a topic that many of you know I like, which is line defects. In some d-dimensional CFT, this will be the object of interest today. The easiest way to think of a line defect is to imagine you have a system specified by some bulk action, and you modify the action or the Miltonian in some codimension d-1 manifold. So this is kind of the way we should have in mind. There's some degrees of freedom localized on a line, which is like a point in space, and this is what the defect is. And okay, this is relevant for many applications. It describes nominal breakdown, it describes impurities, it describes anions, it describes Wilson lines. Of course, I can expand more on it. So something important to realize is that if you accept the idea that the defect comes, so a defect is going to be a picture, that's some RD, and the defect lies in some contour. This is your defect. So something to realize is that you immediately think, even if the action described as CFT or the path integral, if you don't like to think of an action, the defect introduces new couplings, and these new couplings have some new sort of RG. Because in general, of course, even so you tune to the fixed point, the coupling on the bar, the coupling on the defect can run. And so you should ask what are the fixed points of this RG. And the fixed points, which will be the focus of today's talk, are the so-called defect CFTs. I don't know, double bracket. Defect CFTs or DCFTs. Here, this word is just a defect, it's the fixed point of defect RG. And they enjoy an enhanced symmetry. So, so like once you're at a fixed point, there's an emergent conformal invariance. So what can emergent conformal invariance be on a line? The line, when it's straight, has some, other colors. One, yeah.
The whole colored box over there.
Yeah. Okay. Let's do green is fine. So then the coordinate splits into two coordinates along the lines, and coordinates which are transverse. So the symmetry group, the maximum symmetry group that can be preserved by defect in a conformal field theory is bearing additional supersymmetry what is a subgroup of the conformal group, which is just SL2R, which is the conformal group along the line, times the transverse rotation. So I'll assume today that the lines I'll be describing are invariant under this group. The transverse rotation can be dropped, but that's what that defect CFT is. Yes. So again, to just have a very concrete example, which we may or may not discuss in some detail today, is you can take ice in 3D, and then you can consider a defect which is called finite field defect, which is obtained integrating along the line the magnetic field operator sigma. Now, this is a relevant perturbation because delta sigma has dimension which is roughly in 3D 0.5 something. Ooh, I forgot. And since it's integrating along the line, as dimension less than 1, so this means that the energy is close to some complicated defect CFT, of which we can study the properties, for instance, numerically and epsilon expansion of large N.
How do you know it's not trivial in this case?
Huh?
How do you know it's not trivial in this case? It's not on the screen?
This is a relevant perturbation of the trivial line.
Oh, okay.
So, and I'm assuming that the RG on the defect is irreversible. It has been proven, as you know, but I didn't want to go to this level of detail.
And then, so why can't G go to minus infinity? I think, or 0, or whatever. So you start with G equals 1, right? In the trigger line. Why can't it go to 0 and then?
What is 0?
I don't know. Why can't it?
No. Okay.
No, I don't know.
So you okay. Good. This is a very good question. So you need to quantify. Okay, you need an energy monotone to distinguish these different fixed points. So the energy monotone here is the this is a parenthesis. You can define if you compute the expectation value, this of the line on a circle of some radius. This is a sort of a circle partition function, and the logarithm of this. Okay, of this circle partition function. This is by conformal invariance independent of the radius up to counterterms that I don't want to discuss. And then this, you start from the trigger line. So you start in the UV. Here you start from GUV equal 1 or log G equal 0. And then you can flow to some GIR. But I think now we know, I think it's from fancy sphere 0.6, it happened to be. But you can happen, could you have flown to something which goes like 0? Or you cannot rule it out. But the only case where you have G equals 0, there are very pathological cases to describe the inconformal field theory. So
You have an example that flows to G equals 0? Or no?
yes, you can, and but this example will never reach fixed. There are a bit subtle example related modular space and stuff.
G can be negative, right? Or no?
No, G cannot be negative by reflection positivity. Log G can be negative, but G cannot be negative because you cut the circle into your reflection positivity, so it cannot be negative. Yeah, so maybe I should just tell you, okay, the interpretation of this thing, if you have a quantum system on a lattice, is that you have your icing degrees of freedom they live on lattice point, you're turning on a magnetic field as a quantum deformation of statistical, you're turning on a magnetic field only on a single side. Okay, so this is very brief on conformal lines. This was very fast. You should ask more if you never heard this, please. Today I want to discuss something even more perverted. So, I'm discussing line defects, which already sounds something a bit exotic. Well, maybe not in this audience, but some audience may sound exotic. I want to discuss line defects with a cusp. So the setup will be conformal lines A and B that meet at an angle theta. Okay, put these arrows if you know what these arrows are. Let me just put, but it doesn't matter if you don't know what these arrows are. And okay, I want to study this configuration. Okay, this may look like a bit of a perverted configuration to study. Not only I'm looking at conformal lines, which are already maybe not the main focus, but even looking at the cusp angle, but it turns out it's related to a lot of interesting stuff. One obvious thing that this is already not completely exotic, if you do an analytic continuation in the angle, this can describe things like this, where an impurity moves. So now you go to real time after this analytic continuation. And if you draw the icon, and the line moves on, this will describe an impurity that moves first static and then accelerates at some rapidity eta. So it's already something physical to think about, some quench impurity. So the main motivation for me are the following. Already Euclidean is related to interesting observables. These are displacement, if you know what it is, and not per se. Displacement correlators, and Casimir energy, which is the Casimir energy, I just mean the generalization of the Coulomb potential. So when you have two lines that they get very close to each other, you can think of them, imagine these are Wilson lines, like electron and positrons, very heavy, so they exchange a Coulomb potential, and this determines the small angle behavior of the spin, because these have become, I'll explain this in detail, but this is one thing. I already said this well, it's related, at least I should say en passant, it's related to entanglement entropy on cusp regions. So in D equal 3, you can relate calculation of entanglement entropy to calculations of Rayleigh defects.
What is a cusp region?
It just
Is it a couple defect?
Huh?
Yeah, sorry. What is a cusp region?
Well, it's a region where with edges. It's like you draw a region of space-time, something like this.
Oh, okay.
Like rather than drawing a circle, you draw something like that. And then these contributions here are precisely what I'm studying, the contribution from these points in the entanglement entropy. I'm not having anything concrete to say there. Well, all I'll say will apply to Rayleigh defects there, but I won't really comment on entanglement entropy. Already mentioned a quench, and I think to me the main motivation to study this object is this is ubiquitous, this kind of object, in factorization statements. So these are really Lorentzian thing, and really this is about Wilson lines. Ubiquitous in factorization. So maybe this starts two comments. Let me just give you two examples of this. So the first example is that you know that, for instance, E plus E minus production in QED. Okay, QED is not conformal. You can do this in QCD, or you can take some production of particles in some conformal field theory, well, some amplitude, probably define conformal field theory, is IR divergent. So let me just say the production from a virtual photon, E plus E minus, is IR divergent, as you know, by emission of soft photons. So the picture you have in mind is that you're emitting, you have this gamma star, emits E plus E minus. And this is the case like e to the minus a gamma Sudakov times a logarithm, which is basically the mass of the electron, times an infrared cutoff. And the infrared cutoff basically tells you what is the threshold, the number of photons you measure. Because every time you emit a photon, this can be soft, so it can escape you can emit infinite number of soft photons. This suppresses the perception, but if you give some small thresholds photons, you can observe. This is a standard Pascal exercise. This behaves like that. And this gamma Sudakov is precisely the cusp of two Wilson line at angle pi minus I eta, where eta is related to the momentum of these guys. It's an observation by, I think, dates back to 80s or 90s. This is the simplest thing. And of course, this is not in the conformal case, but exclusion perturbation theory is very close to conformal. And okay, anyhow, if you want to really be purist and want to stick to conformal field theory, there is a nice amplitude Wilson line relation. I think this, in the modern language, at least dates back to Aldai, Eden, Korczynski, Baldacena, Sokachev of 2010. A paper I really like, which was very recent, is a paper by Chen, Monni, Pang, and Witten Su that rephrase this in the modern soft effective field theory language. It's a statement that if you take some correlation function, do you see here, or should I go somewhere else? So if you take, for instance, the correlation function, to be concrete, take an equal force over Yamils, take some correlation function of a 4-point function of some bilinear, like trace pi square, and put these points. Yeah, let me just go. Yeah, sure. Let me just go somewhere else. I can just erase. So yeah, let me just rewrite the object. I'm gonna do some 4x1, 4x2, 4x3, 4x4, where O is, say, some, could be a current, could be traced by square, whatever you like, doesn't really matter. And you work in a, so these are your points, you're working in Lorentzian signature. And you work in a regime where these points approach light-like distance. So call this y12, y23, what this distance is y34, y41. You want to be in a regime where we say I plus 1 is small, but what does it mean small in CFT? It means much smaller than I plus 2. So this distance is very small in light recording, but much smaller but compared to the distance between these guys. In this is a Lorentzian statement, so this is everything approaching the light like. And the statement that if you take this object, let's call it G, in this limit, this object is very well approximated by a correlation function of 4 Wilson lines that move at light-like speeds, connecting the 4 points. And these are Wilson lines in their joint. It's not a crazy statement. If you start doing propagators here, you would have propagators connecting these points, dominating at 3 level. The statement is that the most important contribution here comes from exchange of soft gluons between these guys, and the exchange of soft gluons can be well approximated by replacing, by inserting Wilson lines on these things. That's kind of the idea. A more physical way to say it is that, the leading singularity is due to, from the viewpoint of soft gluons, a very boosted quantum looks like a Wilson line. That's maybe the physics. These are, I think, the words of Aldai and collaboration in their old papers. In modern languages, it's proven by a factorization theory, it's proven by soft-Gaussian effective theory. It's not too fancy and more fancier than that. And obviously, this thing here is dominated by the product of the cusps with some logarithms that are also related to these ratios. So the cusp here, I'm not telling you exactly what they are, but basically the cusp in the large Boost limit dominate this object. So, okay. But just to convince you that these cusp lines appear in many, many observables, so it's worth understanding more in general, and also understanding exactly this statement is something that is really interesting.
What do you mean dominating in this? Dominating in what?
It's so this correlator is singular in this limit.
Mm-hmm.
And they said that the leading singularity is given by in the perturbative regime at least.
Or maybe I don't see what's in the law. Is it yi
plus 2 divided yi plus 1.
Oh, okay.
So there is a singularity. It turns out that also this guy goes like log of the same thing. So it's a double logarithmic singularity. So it's not an obvious OP singularity. So this in perturbation theory, it's this Wilson lines that give you the right singular part. There is a prefactor. The prefactor is not given by Wilson lines in general. In any force where you miss, I think there is miracles and the prefactor becomes systematic.
It's kind of exact, right?
In any form.
Yeah.
But in general, this is more general perturbative gauge theory. There is not exact. So in any form is exact. There is also a beautiful relation between amplitudes and Wilson lines. That's far as standardized on the integrated mechanical form. In general, gauge theory, which I'm really interested in, is a factorization statement is the leading singular piece. Okay. So this was very popular, I think, 15 years ago. I think people still use this technology a lot for calculation. Okay, so this is the motivation. It's long, but I think important. Also, it's exact, I think, in the planar limit. Okay, so let me start with the Euclidean analysis. Euclidean cusp. I think I didn't tell you what I assume, sorry, I should have told you that the partition function here, well, I'm going to do now. Okay, so let's look at our object. Lines A and B meet at angle theta. So and let's ask what is this partition function, the expectation value of this thing here. I think implicitly assumed before, but I should explain this. Turns out that if you call this the b of theta, then the log of this, and this also dates back to Sudakov, is a number times a logarithmic divergence, which I'll put an infrared regulator and a UV regulator. So the infrared regulator, you can think of it as a cutoff on the line, and the UV regulator as the way as Moose discussed. This is hardly surprising, because what's going on here is a local feature. A local feature, so it's like a local operator, but local operators, with functional normalization, therefore they have anomalous dimension. I think in fancy language, you can say satisfies the anomaly of this partition function, but I think in really concrete, this is really a functional normalization of this guy. And it's unsurprising. Whenever you insert something local feature in your plot integral, you're going to have UV divergences and you're going to have two anomalous dimension. Okay, so this is really the object I'm interested in today. It's called Cusped anomalous dimension.
Really local, right? What do you mean local? You're changing the boundary.
No. So the divergence is coming here. The logarithmic divergence is a local feature. There are other there is some regular part in this partition function, okay? But this is not going to depend on this UV cutoff, essentially. So the dependence on the UV cutoff here is that.
Sorry, something very naive.
Yes.
Log Z is a free energy, right? So shouldn't you find like a divergence that is linear in the length of the line?
But it doesn't depend on this UV cutoff, so I don't care.
Oh, so there are more divergences.
So these are dot dots. These dot dots is whatever is independent of this UV cutoff. You can subtract it by, you can try to construct ratios to subtract it. That's absolutely fine. But yeah, I think in flat space, but it's also, there are things which are extensive in the line, I agree, but they're not logarithmically divergent. Maybe a slightly better way to see this is to do state operator map. Or well, let's say this is like going to the cylinder. So going to the cylinder, you quantize. It means that you quantize in circles, and then you do a various scaling. So you can think a bit for a moment about it, and you see that this configuration becomes two lines on the cylinder. So here I'm doing a various scaling from RD to R times SD minus 1. And it becomes two lines separated by angle theta in the cylinder. I'm doing a picture in 2D, but this is general. And in this case, the Cusped anomalous dimension is just the ground state energy in this configuration. Now the partition function is going to be just give me the ground state energy in this configuration. So it's EAB of theta by state of correspondence. But because of what Diego said, I also have to subtract the energy of the self-energy of A and the self-energy of B. So it's, okay. There is a 1/2 because I'm inserting well. Let me write it down and explain it. So what is going on here? Once you do this map, you get this configuration. So you can ask what happens if I do this map to a single line. A single line gets mapped to two copies of the same line on the cylinder at angle pi. So that we know shouldn't have any Cusped anomalous dimension if the line is the same. So I need to subtract that from here. So that's where this formula comes from. And the 1/2 is because I'm subtracting half of the contribution from A and half of the contribution from B. Is acceptable? Okay. So this is a way to, again, you can, not sure how important it is for this talk if you're in the cylinder, but it's a good question. I think it's good. So I make one claim I want to make. Let me erase here. Let me make one claim first. The first claim I want to make is that you take the cusp anomalous dimension between a line and itself, and take the second derivative. This is negative. Okay, this is property number one. Okay, so I don't want to. Let me just catch the idea of the proof, and then let me tell you why this is useful. And also, okay, so let me just tell you immediately something. From here, you realize something funny. Since you know that at angle pi, the cusp is zero, because by definition, there is no local feature, it's just a straight line. And since you also know by basically, since the deforming by theta minus theta is the same, by symmetry, also the cusp, the derivative of the cusp at angle pi is zero. From these properties, it follows that the anomalous dimension is negative and decreasing everywhere. Okay, just by integrating this property. So this is already something funny. You'll use that anomalous dimensions are positive. This is anomalous dimension which is negative. It's not a contradiction in any sense, because the symmetry group preserved by the cusp is just a dilation. Unitarity bounds come from the use of special conformal and momentum, so you don't have them, so you don't have unitarity bound that's allowed. But okay, it's just a fact. The proof of this statement is, at least the idea of the proof is elementary. There are some technicalities I think I want to skip. First of all, yeah. Let's sketch the idea of the proof. And it's the idea that basically the cusp at angle theta plus delta theta, it uses a version of locality. The idea is that this is the cusp at Newton picture at angle theta, but then you can also think of a deforming by delta theta as basically doing a small deformation just on one line, okay, and then doing it point tau. Tau is some affine parameter on the line, and integrating this deformation. That's kind of the idea. I'm being very schematic on factors, so don't. If you want, I can be more precise.
The deformation isn't like same at any point, right? So it increases as you go.
It increases, so there is a factor of tau
Okay.
if you want here. It depends actually how you choose the affine parameter.
Right, okay.
You can also think of it in this language. It would be the same language, but that's in conformal filter, that's someone not very important. And then you can think of it, and then the delta theta squared term in this Taylor expansion, you can think of it as a deformation on a line and a deformation on another line at point tau 1 and tau 2. Okay, well, these are infinitesimal deformations, right? And there's an factor of alpha, of course, if you want to read it. But now, and the dots. But now the locality comes in. Locality comes in and tells me, okay, here I'm doing something locally to a line. So the only thing this can be is the insertion of some local operator on the line, which just is a famous operator for those of you who studied NDP, it's called the displacement. It's a protected operator, which basically parameterizes the response of the line to small deformation. In fact, unsurprisingly, it has protected dimension. And its existence is one of the axioms of conformal indifference, or local conformal indifference. So, long story short, so in the end, from here, with some technicality that here you can easily believe, you can kind of see that the second derivative of the cusp is minus, because the cusp is minus the partition function, an integral theta 1, theta 2, some factors of the two-point function of the displacement of this operator on the cusp, where the displacements are inserted once here and once here, so they never touch each other. Okay, because I can always displace a bit this line, a bit this line, that's the second operation. But okay, now that this is the fact that this is gonna be okay. Sorry, I should say maybe the log ZAA. Let me do the log because so this is class. But now this 2-point function has an obvious positivity fact, has an obvious reflection positivity, because I can cut my space into two. And you see that inserting here, integrating, it's a reflection positive configuration. All that is left to do is to check that this indeed gives a log, and that this 2-point function actually is a connected 2-point function converges. Because you have to, and this is done by checking basically the OP of these guys with the cusp at 0 to infinity. This I'm gonna skip.
Why is there no contribution where you deform the same line twice?
You can choose, right? Because you can deform once and once is the same. There's a non-trivial set of world identity if you want to relate these things. I'm choosing the most convenient one so that the two displacements never go on top of each other, so I don't have to worry about short distance divergence. So I'm using some tricks. But yeah, you could write that way. Yeah, so this is the idea that you can relate the deformation to a reflection positive 2-point function. I think, by the way, there are some, I think Ipan and others have some conjecture that actually there are inequalities. Okay, in the context of entanglement entropy, I should say, people conjectured or proved under some assumption that there are this sort of inequalities holds this for the entanglement entropy, but also for Rene defects actually. So also for higher derivatives, but we don't know how to prove them from field theory. So there may be more, we just don't know. But this is what we can prove. Okay, so I want to just apply this quickly to the theta to 0 limit because I promised a connection with Casimir energy, and then jump. I feel like I'm going. Oh, it's okay. I can just show some plots. So, okay, so there is a lot more you can say about the Euclidean setting, but I want to focus directly on the most interesting limit, which is the theta to 0 limit. The theta to 0 limit is best understood from the cylinder. So if you look back at that picture on the cylinder, the two lines now are very close to each other. Let's take it to be equal for simplicity. So what is going on here in this picture is obvious. The cylinder has a natural scale, which is its radius. But here there is another natural scale which emerges, which is the distance between the two lines. Since they're very separated, when there is separated scale, you should expect again to apply effective field theory. And what is the idea here is that now I can approximate this configuration with some effective line, which I'll denote like this. Some C effective. So the idea is now this cusp is basically, if you think of course clearly enough, is the Casimir energy of some single effective line inserted in the cylinder. And a slightly more formal way of saying it is that there is a fusion, that you can consider a fusion between two lines. And this fusion in general is gonna be written in terms of a sum of lines at the midpoint. So A, B, and C are lines. But since these lines are now effective lines, they need not to be conformal, so it will be deformed by all possible deformations. So the first deformation you can write down is the identity operator, and by dimensional analysis is going to come with a factor of 1 over distance. So this is nothing but what would be the Coulomb potential. So this is just a statement here. Charge plus, charge minus, you get the identity line times the Coulomb potential into the minus electric potential 1 over distance. But then you're also going to deform them with all possible operator. And by dimensional analysis, this is going to become with the power theta delta minus 1. All possible operators that can deform this line C. Now you see, I allowed here a sum over lines, but you see two things. First of all, that there is an essential singularity at t equals 0. So really, I should only keep as an effective field theory, at least in the simplest setup, you should only keep only the smallest Casimir energy, because all the others will be suppressed by more essential singularities. Also, I'm deforming with all operators. So which means that these lines here, if I chose here on the right-hand side a line which was not a stable fixed point. Because of this deformation, it will flow to a stable fixed point. So the right statement is going to be approximated by a certain line C prime. The Casimir energy, that line, whatever it is that chooses that. And then there's going to be some only over irrelevant operators because this line will be stable. The sense will not have any relevant perturbation. I guess more intuitive, you could have thought this is just directly a single line, and it's going to be a cosmological constant contribution on the line. It's going to be a relevant deformation. And now, okay, using this thing, it's basically needed to compute this cusp, what the cusp is at small angle. Let me now specialize the two identical lines. This will be the Casimir energy of whatever is the most stable line. There will be an interesting contribution that I'm going to discuss in a moment, which is a constant. And then there will be powers which scale like the dimension of the relevant operators on the line. So you already see an application of that statement over there. The fact that the second derivative is negative tells you that the Casimir energy is negative. So this is kind of a good proof that there's generalized Coulomb potential between a line and its reflection has to be negative. So it goes straight to opposites attract. Nothing. By the way, this was, I should say, you don't need to go through, well, you can also prove this in different ways, but this is one way to prove that this Casimir energy has to be negative. Again, this is, I think, what you expect. And this guy here is the dimension of the defect creation operator. This deserves some explanation. The explanation here is simple. If you think of this effective line and you map it back to flat space, this maps to a line in RD. So it goes from the origin to infinity. So it terminates on a point. But since it terminates on a point, this has sort of a local operator inserted here. It's like in bound BCT. And this local operator has an energy, which is the defect creation dimension, this dimension. And this instead comes from effective field theory, just because of the perturbation. You can immediately estimate that the first correction to this result will depend on the first irrelevant deformation of the line. And that's what it's written down. This is a table expansion. So it should pause here. I think this is not completely clear.
Explain how that dimension equation operator shows up equation above it.
It doesn't show up here from this equation. You have to think that when you use these lines on the cylinder, you don't get a single line on the plane, you get a single line on the cylinder which maps to a line that terminates on the plane.
Oh, okay.
So the diffusion statement is independent of what you do, but when you apply to this setup, you see that you're fusing up to the end. Yeah, I don't want to think it's not very instructive to draw plots in a Blackboard seminar, but I just want to say that many of these statements we checked, well, InChain probe essentially checked them with non-perturbative in the SE model with this sphere method. And in fact, knowing this expansion is kind of interesting because when you do numerics, it's very hard. This is maybe the thing you're really interested in. But when you do numerics, it's very hard to go to small angles. So knowing this expansion is very good to perform fits. So this is a video which I'm doing stuff in this way. And we could estimate this Casimir energy for basically the pinning field in the ISL model. Okay, this is
Sorry, is that delta known from other things, or is it?
yeah, sorry, exactly. So this delta, well, I think we consider derivatives of this guy. So this drops, but this actually known. It was actually known from other things. This is known instead, which is very important, and this is allows us to basically just fit the coefficient here.
For pinning field defect, delta is just a dimension of the field I'm iterating over, or is it something else?
So this is for pinning field defect. Depends what you get plus, and this is the.
I mean the delta C, the constant term.
For pinning field defect is known from the fuzzy sphere.
But it's not the dimension of the field that I'm integrating.
No. This is something else. Something else. It's non-trivial. Yeah, it's non-trivial.
Okay. That's the UV dimension.
Yeah, in the IR, but okay, I guess the question is.
No, but he was asking about this. So the UV dimension, of course, this is delta sigma this is what you would be worried about UV to IR. So delta sigma becomes like 1.6 in the IR, and this is what you're worrying here. But this is really the dimension of this endpoint operator is something else. And already in the epsilon expansions, I don't more than one number. So it's not. But okay, they computed it numerically somehow for this very, very good. Yeah, please.
So here in your proof, there's no local operator sitting in the house.
I assume that I'm on the ground, so it's a very good comment. Yes, so there is if there is a local operator on the cut, you can worry about two things. A, about this cut, because how do you cut a local operator? Instead, the idea is that this is just this defect is just a smooth deformation of the Hamiltonian, so there is no problem with that.
But then in the like 4-point function, there's the picture there is like local operator.
But I mean, here there is no local operator because there is connect smooth at infinity. It's just when I approximate it with this picture, but this is just, I mean, in this configuration here, that argument applies.
Not here, but in the beginning, we mentioned like 4-point four operators correlation function, and that can be approximated as the Wilson line Cusped, the vacuum value of the Wilson line with this Cusped angles.
Mm-hmm.
But that Wilson line Cusped at the Cusped has the charged operator inserted, which is the
So good. But I think what dominates that is still the ground state energy on the cusp.
and even though the local operator that is sitting there, we can still use this.
So first of all, I'm for the case of Wilson, this is not relevant for that setup because that's in Lorentzian. So this is, I don't know what to say, what this is good for that kind of thing. So I haven't thought too much about it. But yeah, so you're right, you can have in that factorization statement, you can have sometimes local operators sitting at the cusp. But I think what happens is that what dominates, the way I think in the end, like what dominates this thing is always just the Wilson line and the ground state cusp energy, the Wilson line. Let me think for myself there some. Yeah, I haven't thought that much on it, so it's a good question. For sure, in the Sudakov that I understand better, you don't have to worry about the operator sitting at the cusp. But I think in this factorization statement, what pops out is really the correlation function of the Wilson line without anything inserted on the cusp. I think that's my understanding of what this pops out. But people studied local operator inserted at the cusp, and okay, then you can ask about that.
I see, sorry, but you compute the Cusped anomalous time in the Euclidean, but you can use that into the Lorentzian.
Yeah, so that is an analytic. Yeah, this is what I'm going to discuss next. I'm completing Euclidean, I'm going to discuss the analytic continuation, and I'm going to discuss the large boost limit, which is relevant for that. Yeah. Okay, so it's very good questions. We are now approaching the Lorentzian setup, so that's very good. So Lorentzian cusp. Okay. So let me just prepare background formulas. I alluded this at the introduction, but this the relation here between Euclidean and log can rotate is and Lorentz is a deep rotation as usual. So you can start the cusp in RD at angle theta. You take theta pi minus eta. So you start with cusp and with cosine theta here, basically between the two lines. And you also, of course, analytically continue time. And the picture you get is this. You get the lines. If you these are the light cones, and the lines move like this. This is dx, and you get basically a space-like configuration with n where the relative cusp angle is. So this is x dot a. Well, this is the cosine of this angle, becomes a cos of theta with a minus. And therefore, I can define the Lorentzian cusp at rapidity eta to be just the Euclidean cusp at angle theta pi minus I theta. Okay? So an important comment here is that once you do the rotation, you might worry about I epsilon and stuff, but you see, as I try to emphasize with this picture, this line is always placed like from this line. So there is never causal connection, so there's no worries whatsoever about this stuff. You can ask, how is this related to more interesting configurations? And okay, that is related by extra-analytic continuation. For instance, the Sudakov configuration I alluded before. What's relevant, for instance, Sudakov calculation is a configuration where the lines are actually time-like. So you can call this gamma Sudakov of eta. And okay, it's an exercise in basically boost and analytic continuation to show that if you insist that the epsilon prescription is enforced everywhere in the path integral, this is related to the configuration to the Lorentz and defined R by something like this, phi minus eta plus I epsilon. That's just what, sorry, what did I say? Sorry, no, minus. Sorry, because we were using a different variables in the notes, so it's like always increase eta minus phi plus I epsilon. Okay, it's not a very instructive proof. We basically have to be sure that you analytically continue the lines from here to here, such that they are always time ordered in epsilon. So that's all there is. And the next analytic continuation relates it to the quench I was alluding at the beginning. So once you know this guy, in principle, you know everything. If you know about analytic continuation, I don't think it's too surprising. By the way, notice that this configuration is, by this analytic continuation, this configuration is real. And instead, this configuration has an imaginary part, and just because this is kind of a scattering process, so there is a phase associated to it. So it's kind of, again, it's very physical. Okay, so what is the idea? The idea is that
Sorry, but it's not a pure phase, right?
no, it's not a pure phase. It has both a real, yeah. So just the real part is the same. So if you only care about the Sudakov suppression, if you want to, then you can just study the S. But you know there is also a phase in the scattering that's also captured by analytic continuation to leading to some leading approximation. Okay, so what? Okay, so something went wrong here. Doesn't matter. Okay, so something that erased from my note. Okay. I think I can go by, I think I remember. So the idea is like what we did in Euclidean case. Okay, we proved the general properties. We don't think much general to say, but we looked at a configuration which admitted some sort of universality. So the idea is to try and do the same here. Let's look for a configuration which has some sort of universal description. And in particular, this will be the configuration eta to infinity, which, as alluded before, has a important application within the context of glitch theories. So in this limit, it's known that if you take the cusp between two Wilson lines, this goes like some small gamma Sudakov is called, whatever, times eta. So it's linear in eta, and this is perturbative in the coupling. Okay. So yeah. So I wanna try to study that in general. And the idea to do that is to do okay. I'll make a claim, and then you tell me how much I should expand of this claim. I'll do first some Lorentz rotation, and I'll do some while. The Lorentz rotation is just for convenience, I'll do some while. And this while basically maps my Lorentzian space to where it is free times SD minus free. And this is actually what it's a slightly defined version of what Aldheim Aldacena did in 2007, if you know this paper. And okay, the while transformation is not very instructive, but it is. If you study defense, you know that going to ADS kind of frames is very useful. And what is the idea? Is that when I do this rescaling, the two lines will be mapped very close to the DS boundaries. But you know, if you know experience with the SFT stuff, which is very close to the DS boundary, it's very weakly interacting in general. So the idea will be to explore this map. And the way you exploit this map is by going some brilliant but somewhat obscure coordinates that were invented by Bellman-Moldasen or applied by Bellman-Moldasen that were invented, which write the ADS free in this way. Okay. So it's not too important you know where these coordinates come from, but the whole intuition is that this metric has two obvious isometries. One is the tau, which you can show is just dilation, but the other one is the gamma, which is boost. So what is the idea? Is that when these objects approach the light cone, they're actually invariant, not under just dilation, which is the only symmetry of the cusp, they're also invariant under boost now, because the boost preserves light-like direction. So the brilliance of Bellman-Moldasen that we're trying to use here is to realize that it's natural to study these objects in a plane which makes these isometries manifest. This will be exact at all times. This will become exact only in the infinite boost limit. So it will play a role of a distance.
Where are the two lines on ADS3?
I'm going to tell you now. So the two lines are move along tau. They are at a snapshot in time, which is the weird thing. So they are like space-like lines. Alpha is the time, and they are only at a snapshot in time. And they are at a distance, delta gamma, equal eta.
So you say they're not invariant under boost, right? When you take
They're all in the limit delta to infinity,
then they're
they become infinitely separated. So what is the idea? You know, if you go, also in the large spin case, it's actually the same idea in that paper. You have two isometries, and one of them is manifest only in some limit. So you go to a coordinate plane where the second isometry becomes a distance. And that's where the physical picture becomes intuitive. So forget in a moment about this statement of Wilson lines that you might know. Then what is it you should expect? When these objects go very far away, these are very far separated, then by locality they should be weakly interacting. So then you should expect that the right statement is that the contribution of this cusp is the sum of two free contributions. Okay, so you have two very far away objects. In fact, actually, you can argue something else. This I'm not going to do. You can argue that interactions in this direction are dominated by the twist. So delta minus j of the CFT. And delta minus j in CFT larger than t larger 2 dimension is always got. It's always larger than 1. You should expect something. So the right state. So I'm going to make. But okay, so these words rely on the assumption that I can make sense of two free lines. But what is, again, a single line here? A single line is a line with an endpoint. Because when I map it back, it's a cusp between a line and a clear line. So let me now make an assumption. Lines admit endpoints. Which is as we showed before, just a state the line can be terminated. Then under this assumption, we basically proved from effective field theory, or argued, that this is this cusp is the contribution of the two free line minus some interaction. The free line contributions, again, you can easily get convinced is the defect creation operator dimension. Creation dimension. And the interaction, you can actually compute it, but okay, for the sake of black hole talk, it's just enough to say that it was like the minimal twist times eta.
what are on map to on ADS? What are you computing on ADS3?
So let me just simplify this. Sorry again.
What are you computing on ADS3?
I'm computing, so I'm just saying, I want to compute this expectation value. This is the expectation value configuration, that's the cusp. And I'm saying a leading order, since they're very far away, is going to be the contribution of two free objects. And then you can identify this with the defect creation operator dimension. And then the interaction. And here is some skipping, but you can argue the interaction is dominated by the twist gap of the CFT, which is the minimum of delta minus j. But here there was a clear assumption that the lines admit endpoints. And by the way, sorry, this talk I'm not really going to do a hard calculation, but this was obviously checked in like 5 or 6 perturbative examples. So just this we can unfortunately cannot do yet, but this theoretically I cannot. It is perturbative will be checked in for a lot of defects. But this assumption is violated by Wilson lines, which are charged under 1-4 symmetry. So Wilson line, the fundamentals, for instance, in an equal force per means are charged, so I cannot make them sense of them separately because they do not meet endpoints. And this actually was the case that was already studied by Dan Maldacena. In this case, basically, it is that this line C at twist zero object, which is the gauge field. So this cusp will roughly be dominated by a flux tube because gauge fields form a flux tube in ABS with a tension times the distance. And this string is what people call the gamma Sudakov. And this is just theta. So you recover the result over there, but you have to remember that the Wilson lines cannot be added.
So what was the logic? So you have a 1-form symmetry, and so
The line it cannot be terminated. I cannot make sense of this individual contribution.
so if you have a 1-form symmetry, where does the gauge field come in?
I think here there is a bit of a step, but the idea is that the two lines now are two parts very separated, and then the gauge field exchange forms a flux tube. And but the point is the crucial point is that the 1-4 symmetry ensures that this flux tube cannot be screened. And therefore the flux tube in ADS leads to this some behavior which is extensive in the size of the flux tube times attention, which is what people compute.
If they give you a theory to 1-form symmetry and no gauge fields somehow, I don't know.
I have speculation, but we don't know.
Okay.
I have speculation, we don't know, so it's better if I don't say it. A more fun thing to discuss is the case where the Wilson lines are not charged in 1-4 symmetry, which is the adjoint, and that's what exactly pops out in these Sudakov calculations. So people perturbative observe a gamma behavior like this, but then this argument suggests that once you take repeat order 1/g², there's going to be a string breaking process, and you're going to jump to a behavior which is constant. It's a non-perturbative effect. We haven't been able to prove it, but it's a speculation that follows just by interpolating between these configurations. So. And this also actually, and I think this is physical because I think this doubly logarithmic behavior of the correlation function we discussed before is not compatible with OP. There should be some sort of transition also at the level of local correlation function that I think people hypothesize. So yeah, it's not crazy, just that this factorization statement are perturbative or planar statement that have to be, this is probably another reflection of that. So I think this is more or less all I wanted to tell you. I don't think, maybe I should add a small conclusion, but let me just write some conclusions. So or summary. Maybe outlook or whatever. So I think so the first thing I try to tell you that cusps are interesting, at least to me. So and they admit, I think the other message is admit universal features under some assumption at least. Features in certain limits, which are theta to 0 and eta to infinity. Yeah, I didn't tell you what this calculation is really good for, but actually you can easily imagine this is kind of if you try to describe the production of an external particle in a conformal field theory bus, this Sudakov tells you about the suppression due to the emission of the CFT stuff. So it's kind of I just wanted to tell you some questions which I think are fun. So I mentioned that there are symmetries that emerge in the null limit. What is their fate? I think here Feder, Justin, and Rajiv had a nice paper, but I think they really focus on the maximally symmetric case. It's known that some of these things have application, at least in any portfolio means. So the question is whether factorization theorems can be revisited non-perturbatively, also using this better understanding of the cusp, which is very crucial there. And yeah, and I think I mentioned application to quantum quantities. So I think that's all. Thank you.
Any questions? What do you mean by factorization? I'm not confused.
So this
And-
this statement that the statement that I was saying before, that the correlation function is well approximated by Wilson line objects. It's a factorization theorem, I think, in modern language. Perturbative HTS beyond any for square universe. Okay, so this is kind of an example.
So it's a large n thing, right?
So no, this is perturbative. This is a perturbative, any perturbative H theory, not even conformal.
Oh.
So this is but there are way more like this matrix align to Wilson lines for factors, in all standard factorization theorem for jets, for whatever people could think is it. So understanding the cusp is, I think, is also towards understanding to what extent these things survive beyond perturbation theory, or actually they should be modified.
You know cases of lines without endpoints, but not because of a one-form symmetry? Is this a thing that happens?
Is it possible? Well, monodromy defects, they are not genuine line, maybe I would say, but yeah. Otherwise,
Improved it, oh, okay, improved it.
monodromy, I guess if you upon gauging, it's the same thing. If you gauge the symmetry, that is for discrete
But you
monodromy.
can prove they don't have endpoints.
Monodromy can, because the monodromy defect that implement a symmetry in a parts of space. So they are attached to a surface, so then it's a cut. So but if you gauge this surface, then it's the same thing. So it's when you can gauge it, it's the same thing. So it's not clearly independent thing. By the way, monodromy defects are often Wilson lines of fractional charge in many theories. So it suggests that going to your question, suggests that at least for some monodromy defect, that behavior should still be there.
You mentioned also this time and entropy. Like, what can you learn something like the time and entropy for like theta equals to 0 limit? Or
So for what? For which limit?
you said you mentioned like also using like time and entropy.
I think so. The statement I claimed about recent concavity, or this the probability derivatives, you can prove them under some assumption for entanglement entropy, and I think also for impurities and other stuff. So expectation value roto DM basically. Using SSA, strong subadditivity condition. So it is like the those some of the statements that appeared before our papers using this entropic argument. And there they have even more statements, but it's not just SSA, they also assume something about infinite divisibility, or someone explained to me. So the implication in mind is that this cusp, they dominate the entanglement entropy as some logarithmic, normally as some singularities around the perimeter, but not as some logarithmic singularity at the cusp.
Right.
And then you can study, they are basically the cusp anomalous dimension of these finite defects in some limit. This is the statement. And
Can you also look at this in time and entropy in the theta goes to 0 limit where they're two like
I don't know. Well, you can. I don't know people. Yeah, I don't know what people have done there.
I
Yeah.
was just curious if you can verify any of the statements.
But I think so. I don't know if they look at theta to 0, but maybe this inequality can be studied numerically by Meng Chang and people out here. So yeah, I don't think they studied the theta to 0 limit much, because it was before our paper. Not study much, but yeah. But theta to 0 is normally very hard numerically. That's my experience. So the question, yeah, I don't know if there's a way to do something analytical.
Nice.
Yeah, please.
What is
What is what?
the null symmetries?
So not symmetry. There was the statement is that so the cusp has only dilation, preserves only dilation among the symmetries of the conformal. But if this become null, so this is because like t equal x, t equal minus x, these are null rays. So boost become an extra symmetry. So this is null. And if you study a single null line, there are actually a bunch of 11 generators in 4D that become. So the question is, I didn't use, in many of these statements that people study, I didn't use any of this, I just used the standard dilation and other thing. But somehow it feels like there is it's useful to think instead of the null configuration of something good on its own upon some normalization, which has extra symmetries. And in equal force Fourier means this was super fruitful because you can actually prove that operators inserted on this null line in some sense which I never understood are basically correspond to states of rotating strings and its relation with integrability and stuff. So this was a very shortcut to say that I think all this story that has been understood in equal force Fourier means is not understood in general.
Right, let's maybe thanks the speaker again.